Just to give you a little background, I am not a software developer. I'm not a web developer officially, but I love to find excuses to do these kinds of things just because I love it. I actually started programming when I was really young, before most of you were born. My first computer was a Commodore 64, but I started to learn to program on my brother's VIC-20 before that. I was an early adopter of Linux. At the time, I did not know I was an early adopter. I was at grad school at MIT, and they had all these workstation computers you could use that ran Unix. And somebody said, hey, there's this version of Unix you can put on your home computer. There's a version of Unix called Linux. And MIT had, like, right there on the computers there where you could put your floppy disks in and take home Slackware. And so in, like, I think it was 1995, I put Slackware Linux on my personal computer. Had no idea I was an early adopter. I just thought it was cool. And anyway, so I've always been interested in computer science, though I chose a different route for my career. I'm a physicist. When I went to college, I knew I wanted to major in some sort of science or engineering. And I thought about computer science because I loved programming computers. But I had a friend who went into computer science, and he just wasn't that bright. And I thought, is that the kind of person who goes into computer science? Okay, now I'm a scientist. I know better than to make decisions based on one data point, especially when that data point drops out of the program a semester later because it was too hard. But by that time, I had learned to love physics. I got into physics. But I'm always looking for excuses to get into programming and do projects. All right, I'm going to talk to you about a piece of software that I developed to teach the physics of musical intonation to students, to physics students. All right, and so here's the software right here. I wrote it in Java because the main reason is I wanted it to be something that anybody on any computer could use. Being a new Java, not having developed a lot of Java programs, I was very naive about that fact. I thought, wow, I write it in Java, then everyone can just use it, right? And it turns out deployment is a real problem in Java. But I think it worked out really well. It's this great program. You can play different notes. You can transpose them, whatnot. You can insert chords. And you can change how this instrument is tuned in ways that normally you can't. All right? I have a little electronic tuner here. It will let me change whether I want to tune to an A440 scale or an A441, whatever. But it just lets me change the root note, moving all of the notes together. Historically, people tuned instruments in very different ways, different than what this tuner will allow you to do. And this program lets you tune this instrument many different ways. It can let you tune it the way they tuned organs when Bach was alive, for example. Right now it's tuned to equal temperament tuning, which is the standard that is almost exclusively used today. Most people, even professional musicians, music professors, hardly ever even talk about any other type of tuning. But here it is. This is the tuning that the world has pushed upon you, all right? And I'm going to play a chord here. Does anybody notice anything wrong with this chord?
Sounds fuzzy.
Yeah, most of you don't. I'm glad you noticed. Most of you probably thought it sounded just fine, right? Because you have been taught to accept the equal temperament scale. Wake up, sheeple. No, I'm kidding. I'm going to show you how you can make that chord sound better. And I'm also going to explain to you why we don't do that. Why it's not always a good idea to try and make it sound better. All right, but to do that, you're going to have to understand the science of musical intonation. All right? One of the things I love about this project is that it's the convergence of a lot of things I love. It involves physics, math, music, education, and programming. And I think I explained before how I feel about programming, but here's you may know some of you may know I have a daily webcomic, and here's a comic I did that explains how I feel about programming. I don't have to work very hard to come up with excuses to write code, all right? In fact, my webcomic was sort of an excuse to write code. I learned how to do web development so I could do my webcomic. It's been a lot of fun. But anyway, one of my loves is music. I love to play guitar. And any of you play guitar? Any guitar players? Yeah? Have you ever been bugged? Has tuning a guitar ever driven you totally crazy? You tune it, right? Nowadays you can use these electronic tuners, right? When I was a kid you couldn't. There are different ways to tune a guitar. You know, one is you go to the piano, you find one note, then you fret up to the 5th fret and get the next note and tune them together. And you do all of that, and then you go and you play, and your chords sound maybe not perfect. And so then the temptation is you start tweaking things and, okay, now this chord sounds great. Now this chord sounds awful. All right? They taught me another way to tune guitars using harmonics. You lightly touch the string here, lightly touch the string here, and they make the same sound. And I thought, this is great. This is scientific because it doesn't depend on where the luthier put the frets on my instrument. This is, you know, fundamental properties of my guitar string. This is going to be better, right? It turns out it's worse. It turns out this is a very bad way to tune your guitar. All right? Probably the best way is to use your electronic tuner, which forces you to use 12-tone equal temperament, which is the system I said before was imperfect. All right? But this problem plagued me as I went on and learned more physics. I found out that what I was looking for was impossible. Perfectly consonant tuning for all chords and all keys just can't happen. And in fact, this is a problem that people have thought about for centuries. Famous people, Helmholtz, Bach thought about this, Pythagoras thought about this, all right, and wrote about this and developed ideas. All right, so I'm going to show you a little bit of the physics of music so that you can understand where musical scales come from, so you can better appreciate people like Bach and the music that they wrote. And there are things they had to think about then that we don't even think about today when writing music. But to do that, I'm going to have to teach you a little bit of math and physics. So we'll start with the math. The math you need to know is pretty simple. You need to know what a sine wave is. All right? You probably saw sine waves when you did trigonometry in high school, if not anywhere else. And you know, it relates to the sides of a triangle to the angles in a triangle. All right? We're not going to do triangles today, but what you should also know is that sine waves, they're things you can plot, right? I can plot sine as a function of theta. So here's theta and here's sine of theta, all right? This magenta line is cosine. So cosines are really sine waves. They're just shifted in phase, all right? So cosines are really just another version of a sine. All right, and it turns out sine waves show up everywhere in nature. So you think, why do I need to know about sine waves? Sine waves are everywhere. For example, if I take a slinky, anyone have a slinky? And I let it oscillate. If you were to plot the height of the bottom of my slinky as a function of time, you know what it would be?
A dampening sine wave.
Yeah, a dampening sine wave, an approximation to a sine wave. All right? Yeah, dampening. We're not going to talk about dampening today. We're going to stick with the simple stuff. Or equivalently, a mass on a spring, right? The height of that mass as a function of time is a sine wave. Things that wiggle tend to be sine waves, all right? I can take my lanyard here, put the mass on it, or maybe I can't. It appears that I can. If I push it, now I've got a pendulum. The displacement of a pendulum as a function of time is a sine wave. So sine waves show up everywhere. Anytime something's wiggling, there's probably a sine wave involved. All right? Okay. And it turns out the sine waves are it's not just one function, it's a whole family of functions, right? So I can plot sine of theta, but I can also plot sine of some constant times time. And when I change that constant, I get a new function, right? So here's sine of t, and here's sine of 1.5 times t. And they both wiggle, but this one wiggles faster. If I plot sine of 2t, it wiggles even faster. Sine of 5t, it wiggles even faster. So sine is really a whole family of functions, all right? Okay, the next thing you need to know is that any wave that I have, any wiggle that I have I can write as a sum of sine waves. And this is just an example. So for example, imagine I have a square wave. These could be pulses of light traveling down an optical fiber, right? This could be a TTL clock signal. I can write that as just by adding up sines. All right? Now, to figure out what sines to add together and how much of them, you do something called a Fourier transform. We're not going to go into that, but here's just an example. If I add all of these cosines together, I can make that square wave. So in order to make the square wave, I have to sum up to infinity. Well, if I just sum up to 1, I just get, you know, 1 cosine. Well, actually 2. I get the 0 and the... I don't have the offset on here. Sorry, there's a typo in here. But anyway, as I add more and more cosines together, eventually it starts to look like a square wave. All right? So this is all the math you really need to know. Sine waves are a regular kind of wiggle, and you can build any other kind of wiggle out of them. Okay? All right. Next, we need to know a little bit about sound. And actually, I'm not really going to tell you much about sound, just that when you hear sound, what's happening is there's a pressure wave. I speak, the air in front of my face gets compressed by my voice. That compressed air is at a higher pressure, so it pushes on the air next to it, which pushes on the air next to it. And eventually, even though the air doesn't, so here's a little, these are air particles, and I colored one of them green, so you can see it doesn't really go anywhere. It just goes back and forth. But the energy travels to your ear. All right? So you're hearing these sound waves, and so there's this pressure that's oscillating in your ear when I talk. All right? That oscillation is not a sine wave, right? It's something complicated. But whatever's happening in your ear, we can think of it as a sum of sine waves. All right? And it's possible to take that signal and figure out what sine waves make it up. And this program, Spectrum Lab, does that for you. This is a free program. I don't believe it's open source, but it's a lot of fun. Only runs on Windows, unfortunately. But anyway, if you take this program, what it does, I'll start the sound thread. And what it does is it listens to the microphone of the computer, and it's plotting here different frequencies, and it's plotting how much there is of sine waves at those different frequencies. I'm going to sing a tone and see what you see. Kind of interesting. Did you notice that the sine waves, the frequencies of the sine waves are regularly spaced? I'm going to pull out a guitar now. Let's see what happens when I play a guitar. You see the regularly spaced peaks there? So when I play a guitar, the frequencies in the sound, we'll go back to this screen here. Here's kind of a picture I took of it. You can see there's some noise junk here. There's a frequency here in my guitar. There's another sine wave at twice that frequency, another sine wave at 3 times that frequency, and at 4 times that frequency, and at 5 times that frequency. So the frequencies in that sound, there's a fundamental frequency and then harmonics of that are just integers times that frequency. All right, so that has to do with the resonance of my guitar string. So looking at my guitar spectrum, what's really happening is there's very special ways that my guitar string can oscillate that are known as modes. All right? The top one is known as the first harmonic, or the fundamental mode of the guitar string. And it oscillates back and forth. And the string looks like a sine wave, right? It's just getting bigger and smaller, oscillating up and down. And then there's the second harmonic, which oscillates like this. And it has a frequency which is twice the frequency of the first harmonic. Here's the third harmonic, the fourth harmonic, and there's just all these harmonics. Now you can do something interesting with your guitar. If I play a string, if I lightly touch the string right in the middle, get here so you can see what I'm doing. Did you hear the frequency go up? So what's happening is when I pluck this string, I'm exciting all these different modes. What's happening is a sum of these different modes. If I put my finger there lightly, I damp out this harmonic, but I don't damp that one because it's not moving there. And I don't damp this one because it's not moving there. So I can find the harmonics on my guitar string. If I touch it right here, I can damp the first and second, but keep the third harmonic. Oh, sorry, right here. So that's the frequency of the third harmonic. It's 3 times the frequency of the fundamental. All right? Now, it turns out I can figure out anything that my guitar string can do by just thinking in terms of adding these different harmonics together. So by adding together all of these oscillations with the amplitudes given here, I get a simulation of what happens when you pluck a guitar string, right? I pluck it here, I disturb the string, and that disturbance zips back and forth on the string. All right? I made a more realistic simulation as well. It turns out on a real guitar string, the frequencies of these different modes are not exactly an integer times the fundamental. They're very, very, very close, but they're a little bit different. And if you add that in, what happens is these different waves get in and out of phase with each other, and you get a more complicated motion of your guitar string. Yes?
Just as connecting back to what we've already learned, would they become integers, like exact integers, if you use a different tune?
No, this is a property of an individual guitar string. So if I tune it to different frequencies, the fundamental changes, but they all move together. The reason they're not exactly integers has to do with the stiffness of the string, that it takes energy to bend the string even if there's no tension on it because it's made of steel. A classical guitar is much, much closer to a pure harmonic series because the strings are more flexible. But they're really, even this guitar string, they're really quite close. Yes?
Is the actual sound wave being produced as a result of interference, or is it actually producing that wave?
Yeah.
itself?
That's a good question. I wasn't going to talk about this, but it's one of my beefs about music, actually. I play the string, and it's doing this crazy oscillation. The string is moving air, all right, and makes a sound. But it doesn't make a very big sound because it's a very tiny string, and it doesn't move a lot of air. And that's what the body of the guitar is about. The string moves, and it wiggles the bridge here, and the bridge moves the top plate up and down. And so you have a much bigger area. You know, and the inside of the guitar, as you move the air in and out, it moves in and out of the sound hole. And so it couples that vibration to the air more efficiently. If you talk to acousticians, they'll talk about the body of the guitar being a resonator. It's not a resonator. I mean, it has resonances. Everything has resonances. But that's not its purpose. Its purpose is to be an antenna, to couple that vibration to the air. And to illustrate that point, there's a type of guitar that instead of having the top plate move, the bridge sits on top of something that looks like a speaker cone. And the speaker cone moves up and down when the guitar string vibrates and it emits the sound. Ironically, that type of guitar is known as a dobro. It has a more common name. Does anyone know what the common name of a dobro is? It's a very ironic name. It's known as a resonator guitar. So the guitar that proves the guitars really aren't resonators, the guitar bodies aren't really resonators, are known as resonator guitars. Anyway, that's a little personal beef I have. But anyway, yes?
So clamping the body, like if you were to really isolate the body, the sound would be almost shut off.
Has anyone ever heard an electric guitar without amplification? An electric guitar, the body is solid. It's designed not to vibrate. And you can hear sound when you play an electric guitar, but it's very quiet. All right? Unless you plug in the pickup to the amplifier. All right, it turns out other instruments also have harmonic series. I brought another one here. This is a tin whistle. I am not a tin whistle player. All right, but here it goes. I'm not very good at this. The hard thing about this is how you play it, how you blow it determines which harmonics get excited. So if I blow a little harder, I can basically eliminate the first harmonic and see higher harmonics. I play it softly, we see a harmonic series, but watch what happens when I blow harder. So when I blow it harder, the even harmonics pop up more, and it sounds an octave higher. All right? The reason I wanted to bring a tin whistle is because I couldn't bring an organ pipe in. And a tin whistle is a lot like an organ pipe. And it turns out organs have a lot to do with the history of intonation. All right. So let's go back to the talk now. All right? Okay, so other instruments have harmonics too. Organ pipes, trumpets, violins, saxophones, and so forth. The last thing you need to know about physics before we can start talking about music is beats. Anyone play in an orchestra or a band? You guys know about beats? What do we do with beats? Yeah, we try and get rid of them. If you're playing out of tune with somebody, you'll hear these beats and you try and adjust your pitch to be in tune with everyone else by getting rid of these beats. So the basic idea behind beats is, imagine I have two sine waves. Here I've got two sine waves. This one is a little bit higher in frequency. So you see over here, this one is in phase with that one. They're both going up at the same time. They're both going down at the same time. So if I add them together, I get a big oscillation. But a little while later, this one has oscillated faster. So by the time you get over here, you know, you're looking and you're saying, this one's going up when that one's going down. If we add them together, they're just going to cancel each other out. So when I add these two waves together, you get times where it's very loud, times where it cancels out, and then it gets loud again as they get in and out of phase with each other. And we can actually hear that. All right? So here is a sine wave. Anyone know what a sine wave sounds like? You're going to find out today. This is as close an approximation as my computer can do to a pure sine wave at 440 hertz. All right? Here's a pure sine wave at 442 hertz. Sounds very similar, doesn't it? But what happens if I play them together? Do you hear the beating as they get in and out of phase with each other? All right, it turns out that the rate of that beating is just the difference in the frequencies. We heard 2 beats per second because the frequencies differed by 2 hertz. What will happen if I play a 440 hertz sine wave alongside a 550 hertz sine wave? I don't really hear a lot of beats in that. What I hear are 2 different tones. Yes?
Would that be because they are both harmonics of 110 hertz?
Yeah, well, actually, no. If this were an organ playing with lots of harmonics, and we'll talk about that in a minute, it would be. And we'll talk about that. But for pure sine waves, the point is there is beating going on. But it's beating at 110 hertz. All right? Your ear hears that, and your brain interprets that. If the frequencies are very close together, your brain says, that's one sine wave getting louder and softer. But as those frequencies get further apart, your brain says, no, that's not one sine wave getting louder and softer. I recognize that as 2 independent sound waves, and you hear a chord. So if they're really close together in frequency, your brain hears beats. At some point, I wish I should have brought a program where I could change the frequencies continuously. At some point, your brain starts to say, no, those are 2 different notes. They're 2 different frequencies. Yeah? Is there a question over here?
I was just going to say, it's far enough apart that our brain interprets it.
Yep. So yeah, your brain is involved here too. There's a lot of psychology involved in music. All right? Okay, so...
Would that switch point be where we actually can hear frequencies? Like, we can hear 20 hertz, right? That's our limit. Would that be where it is?
It's not a fixed frequency as much as a fixed ratio, I believe. I'm not really sure. I can't answer that question concretely. I'm not sure exactly how far apart they need to be. I should go home and do an experiment and see what I can hear, actually.
Hear, like higher pitches.
Yeah. Yeah, but I don't know how that. I don't know if their ability to distinguish 2 different ones change. And it is a little different from person to person. I know that. Okay, awesome. Let me know. Okay, so now we're moving on to music theory. If I play a guitar string, boom, you hear a sound, all right? What your brain is doing, your brain is hearing all these different sine waves. Why don't you hear lots of notes? It's because your brain knows about harmonic series. It hears all these sine waves and it says, this is all part of one instrument. I know that. I recognize that. So your brain says, here's the lowest frequency in that harmonic series, the fundamental. And that's what your brain interprets as the pitch of the note. All right? So if you play different instruments, you know, if the fundamental frequency is the same for different notes, your brain will say that's the same note. They're playing the same pitch. Your brain uses these higher harmonics to tell you about what kind of sound it is. For example, is this a saxophone? Is this an organ? Is it a trumpet? Is it a guitar? So your brain looks at those higher harmonics, and those give the tone of the sound, whereas the first harmonic usually is what your brain picks out as the pitch of the tone. All right? So if I go back to my program, and I play a C, and I change the instrument, your brain said that's the same note, but 2 different instruments. They had the same fundamental frequency, but the size of the different harmonics were different. All right? That's one of the things your brain uses to determine which instrument it's playing. Okay, the next thing you want to know about music are intervals. All right? So here's my piano keyboard. I take any 2 notes, and that's an interval. So the interval is just the distance between 2 notes. All right? One of the most important intervals in music is the octave. An octave takes us from one A to an A an octave higher, or from one F sharp to an F sharp an octave higher, or from one C to a C an octave higher. All right? That's one very important interval. All right? Now I have plotted here the frequency of the notes on the pitches of the notes on a piano. And what you see, so here's the frequency of the fundamental as a function of note number. And what you can see is it's not a straight line. So if I started at note 20 and went up an octave to note 22, there's 12 notes in an octave, all right? The frequency changes by that much. But if I start at note 70 and go to note 82, the frequency changes by that much. It changes by a different amount. So when I tell you I'm going to change by an octave, I'm not telling you that I'm changing by a fixed frequency amount. How much the frequency changes by depends on where I start. So when I change an interval, when I go up an interval or down an interval, I'm not going up or down by a fixed amount of frequency. It turns out what I'm going up by is a fixed factor. So it turns out that going up an octave in most scales is going up by a factor of 2. So if I play A440 and I go up an octave, what will the frequency of the A above A440 be? 880. And the one an octave down will be 220 hertz. All right? OK, so the octave is one interval. You take any two notes on your piano, and some musician will be able to tell you a name for that interval. All right? Intervals that are going to show up later on in this talk are the fifth. All right, the fifth is 7 half steps. So we go 1, 2, 3, 4, 5, 6, 7. So it takes us from a C to a G, or from a D to an A. All right, and that's a fifth. That's a very important interval in music. Another very important interval in music is the major third. It takes us up 1, 2, 3, 4 half steps. All right, so start anywhere, go up 4 half steps, you have a major third. All right? Okay, another thing you should know about intervals is intervals can be just or they can be not just. What do I mean when I say an interval is just? A just interval is one where that frequency factor, you know, the factor we go up or down by, can be written as a ratio of small integers. So if I go up by a factor of 3 halves, that is a just interval. Yes? I will not do that, all right? Because this is all about what's going on inside your head and what you can hear. I've heard some, I guess anciently, people kind of decided that they would call it a just interval if the intervals were 6 or smaller. But it's really, there's not a really sharp dividing line. I've played around with it, and I found that 6 seems like a pretty reasonable estimate for the way I hear things. But I'm not going to put a definite limit on that. All right? What is not just? Pi. If I go to A440 and then I make a note which is pi times bigger, right? I can't write pi as a ratio of small integers. That's not just. If I take the ratio of 2 large primes, that's not a just ratio. All right? Now, why do we care about just ratios? I think I forgot to read the line up there that it turns out that music sounds nice if we have just intervals. All right? We use 2 terms, consonance and dissonance. A consonant chord or a consonant interval is one that sounds pleasant. You know, maybe you could fall asleep while you're listening to it. A dissonant chord or a dissonant interval is one that maybe makes you a little edgy, makes you want to scream at your kids, right? Okay? And music, people, for a long time, people like Helmholtz, mathematicians, musicians, have figured out that just intervals tend to sound more consonant. Why is that? All right? Well, I'm going to show you that with some pretty graphs. So here I've plotted a harmonic series. This isn't something I recorded. This is just something I made up in a math, right? All right, in Python and plotted it. So imagine this is the spectrum of an organ pipe showing me which frequencies are being played. The root of this note is 220 hertz. Now imagine I have another organ pipe that makes a similar spectra, but it's tuned so that its root is at 330 hertz. We plot both of them together and we see these 2 harmonic series, right? Notice something interesting. If I look at the 1, 2, 3rd harmonic of the lower note and the 2nd harmonic of the higher note, they're at exactly the same frequency. All right, let's zoom in on that. There they are. They're right on top of each other. So when I play each organ pipe, I get a whole bunch of sine waves from each pipe. Those 2 pipes, when I play them together, there will be 2 sine waves right on top of each other. If they're exactly the same frequency, I won't get beating. They're the same sine wave, right? But now imagine, if you will, what if my 2nd pipe was tuned to have a fundamental that was not 330 hertz. It was 327.91 hertz. All right? So with 330 hertz, why did they line up? Because my harmonics are integers of the fundamental frequency, and the factor I went up by was a just interval, factor of 3 halves. But if I go up by a factor of, I don't know, some not just interval, I get this, right? And you notice these 2 harmonics of these 2 notes don't quite line up. Let's zoom in on them. So they're not quite the same frequency. So what am I going to get? I'm going to get beats. And I can demonstrate that with my program. All right? I'm not going to explain to you yet. I will explain later what the tuning thing is that I'm selecting here. Let's do this one first. All right. So I'm going to turn on the advanced options, and that will allow me to display the frequencies of all the notes. I don't know if you can see that on there, but if we look at the frequencies here, here is 220 hertz. That was one of my notes, right? And the other one was 327.91. Do you hear the beating? Okay, now I'm going to turn that into a just interval. I'm going to make this one be exactly 330 hertz. Which one do you like better, the first one or the second one?
Whoa. I actually like the first one better.
I guess it depends on what you're going for, right? If you're playing bagpipes, this might be kind of a... Why did they make bagpipes? They made bagpipes to make people want to yell at their kids, right? You're supposed to intimidate your enemy. They're supposed to sound like this. But if you're Bach and you're writing a piece of music for church, you probably prefer that, right? Because this is a just interval. It sounds really good. All right, so the scale that we use today is known as 12-tone equal temperament, or 12-tet, all right? And the way 12-tone equal temperament works is we define the octave to be a factor of 2, and then we divide the octave up into 12 equal steps. So each time I go up a half step, I want to multiply by something such that once I've done 12 of them, I get something a factor of 2 higher. So that means that each half step, if I start at A440, if I go up a half step, I'm going to multiply by 2 to the 1/12th power. 2 half steps is going up 2 to the 2/12th power, all right? So it's just mathematically divided up, just like it's shown here, all right? So if I define this note to be some frequency, I can find all the other notes with these 2 to the 1/12th steps, all right? And I can get all these different frequencies. Now, yes?
Extending that past 1 octave, would it be 2 to the 13th?
2 to the 13/12th, yeah. Any note that I can find here, I can find one an octave higher by multiplying by 2. Yeah, so it would be 2 to the 13th, 2 to the 14th, 12th. So you can just keep going up. All right? Now, the interesting thing about equal temperament, there's only one possible interval that you can play that will be just, and that's the octave. Everything else won't be just. So that's why you hear beating. Go back to my program. If I go to equal temperament, and I play a C chord, all right, you can maybe notice some beating. If I go to a perfectly just chord, sounds very different. No beating. Beating. All right, so equal temperament involves beating. It involves dissonance. So why do we put up with it? Well, let me show you what we had before we had equal temperament. The earliest known tuning scheme is known by Pythagorean, as Pythagorean tuning, and it was developed by Pythagoras. And he had a problem. Back before you had electronic frequency synthesizers and tuners, how do you generate known frequencies to tune your instrument to? All right? Well, Pythagoras realized you can build a 12-tone chromatic scale with just 2 intervals, the octave and the fifth. With just those 2, you can get all of the notes that you need. And so in Pythagorean tuning, we define the octave to be a factor of 2, and we define the fifth to be a factor of 3/2. This is known as a just fifth because it's a just ratio, right? It ought to sound very consonant. So how does Pythagoras, way back then, come up with a way to generate these intervals? With harmonics, right? I take my guitar string, I touch it halfway up the string, and I can hear the second harmonic, which is a factor of 2 above the first harmonic. If I go over here, I hear the third harmonic. The third harmonic is a factor of 3 higher in frequency than the fundamental, which means that the second harmonic and the third harmonic differ by a factor of 3/2. So here's my fifth. If you ever want to know what a fifth sounds like, just remember Star Wars. Star Wars, wonderful Star Wars, right? I can do that in any key. Star Wars, wonderful Star Wars, right? That's a fifth. So I've got a physical device I can use now to generate my octaves and my fifths. And then I can use that to make my whole scale. How do I do that? Oh, before I tell you how, when I play this fifth, there will be no beating. It is a just fifth. It will be perfectly consonant, all right? And I'll show you that in a minute. All right, and we can get those intervals using harmonics on my guitar string. All right, so here's how it works. So imagine I define some note, all right? I start with some note. I'm going to set it to some frequency. If I go up a fifth, so I've got my C. If I go up a fifth, I get my G, right? And I just use my harmonics, and this note becomes a factor of 3/2 higher than my root note. If I go up another fifth, I just have to take this and multiply by 3/2 again, and I get the D. All right, if I keep doing this, I'm going to go off the screen. So let's take this D, and let's find the D an octave lower. How do I do that? Divide by 2. So I divide by 2. This note is a factor of 9/8 higher in frequency than that note. And I can just keep going up in fifths. Every time I get too far, I'll cut down by an octave by dividing by 2. All right. Eventually, I get to this F sharp. And you look at that and you say, those are not small integers. And as I keep going, the integers are just going to keep getting bigger and bigger, right? Yeah, so I've got a power of 3 over a power of 2. They're just going to keep going up. Yeah. So instead of keeping going up, what we're going to do is we're going to go back to our root note, and instead we're going to go down in fifths to get the rest of the notes. All right? So I'll take my root note. I go up by a factor of 2. Now I have my octave. And let's just start going down in fifths. So if I go down, I get the frequency of the F. Go down again, bop that up an octave, and I just keep going down, and I fill in all the rest of the notes. So now I've filled in all of the notes. All the other notes I can get just by multiplying these by a factor of 2 to get the octave, right? So there you have it. That's how you define a Pythagorean scale. And it's got a lot of just intervals, right? If I play these two notes or these two notes, they ought to sound really nice, right? Or these two notes, that's fairly small. All right? OK. So why don't we use Pythagorean tuning if it's so great? Well, one problem with the Pythagorean tuning I can show you, we went up 6/5 to get a bunch of the notes, and then we went down 5/5 to get a bunch of the notes. What if I go down one more fifth? I'd land on the same note, the F sharp, right? I get to the end, and I do. There's my F sharp. Let's bring it up an octave. Oh, we don't get the same frequency. Right? So you can think of a scale, a chromatic scale, as a clock. It's got 12 pieces, and we can go in steps around and get all of the numbers. All right? But we have to have the right angle between each of those numbers if we want to end up back at 12 again when we're done, right? So the correct number is going up by these factors of 2 to the 1/12, right? That's what just intonation does. It divides things up equally. We didn't do that. We chose a different definition from the fifth, right? We chose 3/2 instead of 2 to the 7/12. So we're going not quite the right distance. So when we get to the end, we don't quite end up on the 12 again. So it turns out we get two definitions for this note. Any musicians ever heard anyone say something to the effect of, an augmented fourth is not the same as the diminished fifth? This is what they're talking about. There's really two F sharps. All right? Yes?
So why didn't you define a fifth as 6 half steps? If in the Pythagorean...
Well, see, the point was they were defining what I mean by a fifth is 7 half steps. What frequency, what ratio do I define those 7 half steps to be? The mathematically correct thing to do is to say a fifth is 2 to the 7/12. All right? But Pythagoras says, no, we can get these harmonics. Let's use 3/2 because we can get that physically, and it makes things nice and consonant. All right? So there's one problem, that the scale doesn't quite meet up. Because of that, if I play a fifth, so if I play a fifth from here to here, it'll sound very consonant. If I play a fifth from here to here, it'll sound very consonant. But the fifth rooted in my F sharp actually ends up involving a ratio that looks like that. It's not consonant at all. And this is known as the wolf fifth because people thought it sounded like the howling of a wolf. All right, with my software, you can hear that with your ears. All right, so let's go to Pythagorean tuning, and I'll play a fifth. And let's go up in half steps. Sounds okay to you?
Ooh.
All right, I'll turn that off. OK, so that's a problem with the Pythagorean tuning, that all the fifths sound consonant except for one of them. It sounds really, really bad. Also, other intervals can involve big intervals, like the major third. There's 2 different major thirds you can get depending on where you start, but they're both fairly large integers. You get a lot of beating in those thirds. And it turns out the major third is very important in music. All right? And intervals sound different in different keys. So if Bach writes this nice piece of music, knowing which intervals sound bad, being very careful not to, touch those intervals, and then the singer comes in and says, that's just too high for me. Can you take it down 3 half steps? boom, now his piece is ruined. All right? Okay. When Bach was alive, people didn't really use Pythagorean tuning as much as another type of tuning known as mean tone tuning. But mean tone tuning is basically Pythagorean tuning, except we temper the fifth. We start with the fifth, and I say, I'm going to tune it up or down a little bit, and introduce a little bit of beats to try and make other things sound better. All right? In particular, the type of tuning used in Bach's era was known as quarter comma mean tone. Quarter comma mean tone adjusts the fifth to be a factor of 5 to the 1/4. I don't know that Bach thought of it that way. It's 5, the fourth root of 5. But what it ends up doing if you do this is now you don't have just fifths, but most of your thirds are now just intervals. All right? And since the third, I guess the thinking was that the third is a more important interval in music than the fifth, so let's make our thirds just. All right? However, quarter comma mean tone actually has no just fifths, and the wolf fifth is even worse than in the Pythagorean tuning. All right? Plus, as before, if you play a song in different keys, it will sound differently. So let me show you quarter comma mean tone. So here's our fifth. It's not just anymore. There's a little bit of beating. And the wolf is really bad. But if I play a major third, it's just, right? If we did things with Pythagorean tuning, it would sound like this. Not great. All right, so that was their compromise. They said, let's make our third sound good, even if it makes our fifths worse. All right? Okay. One cool thing about tuning an instrument to quarter comma mean tone is you can hear what a song would have sounded like played by Bach on an organ from Bach's era. So my program allows you to load MIDI files. So we'll load up Bach's Passaglia in C minor. All right? This is what it would sound like on an organ built today. And we're going to jump to where there's some actual chords. Now I'm going to tune this instrument the way they tuned instruments in Bach's day. Oh, whoops. They used a D root. Here we go. It sounds a little bit different than you're used to, right? In equal temperament. It's kind of hard to do in a classroom, but you can download the software. It includes a bunch of MIDI files, including this one, and you can play with it. My wife is not a musician, and when I showed this to her, we played it in equal temperament, and then we played it in quarter comma mean tone, and she's like, wow, that sounds really a lot better. That's really, oh, gross, right? So until you got to that, a lot of chords sounded really good, but some of them sounded really bad. One nice thing, though, is that if you're Bach living back then, you have to worry about what key things are in, what intervals you can use. You can't just say, what sounds like a good tune? You have to stop and say, that chord is going to sound horrible. I can't use that chord. It made writing music a lot harder. But at the same time, he had different things he could do. If he wanted you to be angry, he could throw in a very dissonant chord, and then he resolves that, and you're like, oh, right? So you could play with your emotions a little bit more using the dissonance and the consonants. All right? Yeah. Oh, thank you. That was one thing I meant to do that I forgot to do when we got started, was plug my computer in. Yeah. Thank you for cluing me in on that. All right, there we go. And now we're going to be high performance, too. Okay. On the other hand, so there's benefits of quarter comma mean tone. But on the other hand, if I play a more modern piece, more modern, not really modern, here's Clair de Lune. It's a very chromatic piece. If you play this in quarter comma mean tone, you can't choose a key to play it in that will make it sound good because it's always changing keys. Whoops. Let's speed that up a little. Oh, that sounds okay. That doesn't, right? Wow. So, problems. Another thing you might be thinking is, why do this? Why not explicitly just set all of the notes to be just ratios? And people have done that, all right? And I can show you one of these perfectly just scales where you just sit down and you say, I'm going to make every one of these notes a small integer ratio. Yes?
Does that mean for that every note is a different frequency in a different key?
So the note, I don't know how to. Okay, so each note has a different frequency, right? But if I go from this note to this note, it's a factor of 5/4, right? But if I go from this note to this note, which is the same interval but in a different key, starting on a different root, I get a different ratio, right? So each note on my piano has a certain frequency, but when I play songs in different keys, the intervals have different frequency ratios between them, all right? So Pitoni came up with a scale where everything is explicitly a just ratio, but it's only true in one key. So I can show you here. Let's go back to our beloved equal temperament. Let's play a C major chord. And you can hear some beating. Now we go to Pitoni's. And let's tune our root back to C. Okay, sounds very good. Sounds not so good. But if I go up in half steps in equal temperament, each major chord sounds equally bad in equal temperament. But watch what happens when I do my just intonation. All right? So here I play my C major chord. Much more consonant. But now watch what happens. All right, so the point is, this is just impossible. You can't make all chords consonant, all right? So it sounds great for chords based on the tuning root, but. So today what we use are compromise scales. All right, so Bachs was a big proponent of compromise scales where you intentionally introduce dissonance into some intervals to reduce dissonance in other intervals. And what we use today is this equal temperament I discussed earlier. Equal temperament has a fairly unjust third. A lot of people complain about that because that's probably the most important interval. But it sounds the same in all keys, so people run with it. So I got just like a minute. I'm going to tell you a little bit about the code. So this project is based on MIDI synthesis. I wanted you to be able to actually hear what it sounds like with actual sounds. If you use just sine waves, you don't have harmonics to overlap and beat. And my program actually will let you play sine waves, and you'll see that those beats disappear. You can also make sine waves plus harmonics and add in harmonics. But the original goal was to let you hear what this sounds like with real instrument sounds. So I used something called MIDI synthesis. Looked on the back of my electric piano at home. It's got these cables. MIDI was defined as a protocol for musical instruments to talk to each other. So you can hook your keyboard up to a synthesizer. It doesn't send waveforms, it sends musical events. It says, turn this note on, turn this note off, and whatnot. All right, and we're short on time, so I'm going to whip through this. But basically, every computer comes, pretty much every computer comes configured to play MIDI files. All right? In the old days, they used them for background music in games. If you have like a music notation software, it uses MIDI synthesis because it thinks in terms of notes, not waveforms. All right? Unfortunately, the MIDI standard does not explicitly define how to do tuning. There's some hints, but a lot is left up to the instrument manufacturers or the programmers. Oftentimes, tuning is just not implemented at all. So what I did is I used pitch bend. So what I do is I take the notes and I move all the C's to one MIDI channel, all the C sharps to another channel, all the D's to another MIDI channel, and then I apply a pitch bend to each of those channels that's just right to obtain the tuning that I want. All right? Okay, it's a free open source software. I decided to go with the MIT license. The reason I chose to do that, it's not what most people like GNU or Creative Commons stuff. On my webcomic, every now and then I'll need like a font or I want to put some picture in. And I love it when people put things out there that are free to use, but most things have this like attribution thing. It's like, I've got a comic this big. How can I say image from blah, blah, blah? It's just annoying, right? And I don't want anyone to run into that trouble, so I decided to use the MIT license, which basically says, this software is free. You can do anything you want with it. Don't blame me. All right? So it's pretty much what it says. So it's not quite in the public domain, but it's as close as you can get and still have some sort of a copyright on it. All right? One thing I wanted to ask you about, right now, the name of the program, the working title is Mod MIDI Tuning. One of my colleagues said that's a really crappy name. So I need to come up with another name. If you have any ideas, if you like any of these up here we thought about, I'd love your feedback. My favorite is Just Beat It. But that's not really going to work, right? No one will get the double pun there. So then I decided detune sounds good because we're detuning these notes to do different tunings, and my name starts with D. I did a Google search, and you search for detuning, you get all kinds of pages on the detuning of a guitar. There's also a techno group called Detune. Didn't want to have that conflict, so then what I'm thinking about now is Y-tune. I did a Google search, didn't find anything. It sounds kind of like iTunes, so that makes it cool, right? The Y stands for BYU, which is where I developed the software. Also, when you say it, it's a common question that amateur guitarists say all the time. All right, so I'm going to leave you with a comic and a link to the software so you can go and play with it yourself. It's got help files that tell you a lot of the things we talked about today. All right?
Are you going to put these slides up?
Oh. Is there somewhere I can put them? Okay, I'll have to go to Joined In and post the slides. The slides are right there. You can use this QR code to get to my slides. The slides that are currently uploaded are a little different from what I have now. I'll make the changes on Monday when I go into work. Yeah, and if you download the slides, anyway, you'll have the link to the software too. All right?
Are some of your animations open source as well?
Some of my animations.
For syllabus and also my teacher class?
Feel free to use any of the, I mean, the comics have copyright on them, but like the sound waves, whatever, any of the plots or things I've put on there, feel free to use in an academic, whatever, or wherever you want, really. Yeah. Huh?
You and Eric could pick up about 20 beats per
20 beats per second, so wherever you start, it's 20 beats per second that matters.
That when it starts cutting off and then start thinking, that's 2 notes.
Okay, so that means an interval played in a lower octave and a higher octave, your ear will maybe in the higher octave where the beats are faster, you'll hear something different than when you play using the same tuning. I did not know that. That's really cool. Thank you.
That does coincide with the lowest frequency.
That does. It's kind of cool.
Sir Wade, 8th edition or something.
Awesome. Well, thank you very much. And if you have any questions, come talk to me. If you have any questions, you can talk to me, but I'm not going to keep everyone from lunch.